The Dirac Delta is a confusing topic, and it's made more confusing than it really needs to be. So I want to just briefly explode a couple of myths about the Dirac Delta. Notice I'm not calling it a function. I'm sure your instructor warned you that the Dirac Delta is not a function, but then they proceeded to pretend as hard as possible that it was, and caused a significant amount of confusion, I'm betting. I had to hunt through books to figure out the theory of generalized distribution so that I could really understand what was going on in order to solve some problems that were assigned in my quantum mechanics textbook. And eventually I realized the sentence no verb. Some of the questions weren't even wrong, they were incoherent. So let's try and clarify a little bit. Here's just a couple of points that hopefully will help you out. Here's a myth. The Dirac delta is 0 when x is not equal to 0. That's complete garbage. That is not true at all. It's not even wrong. It doesn't make sense. Because the Dirac delta is not a function. It doesn't have values at all. There is no such thing as delta of 3. It doesn't exist. It's not a function. It's a gibberish symbol. So why do they say that? And why do they ask you to prove it in books? They say, if x is not 0, then delta of x is 0. It's kind of like saying, dogs quack. Well, if by dog you mean cat and by quack you mean meow, I suppose, but it's not like you're helping anybody understand anything. The Dirac delta is not defined by values. It's defined by integrals. Okay, so this statement is gibberish. What's something that does make sense? Well, your instructor may have mentioned that the Dirac only makes sense when it's integrated. If you have something like this, okay, that has a meaning. In fact, you could shift the function over and say that if you want a spike, so to speak, at x equals c. This is a function. It is a function of 3 variables, and none of them are x. This thing equals 1 if a is less than c is less than b, and equals 0 else. So that is a function. What does this have to do with it, quote, being 0? It means if you were to take the 0 function, 0 the function, not 0 the number, and integrate it, you get 0. This is 0 the function. This is 0 the number. This thing has a graph. It is a horizontal line on the x-axis. This thing is just a number. That's one of the problems they have, is they are constantly confusing different kinds of 0 when they're trying to talk about this. So what they're saying is that if you have intervals from a to b, and 0, say, is not between, let's say c is less than a, or c is greater than b. If you take the integral from a to b of delta of x minus c dx, that does equal 0, the number, so long as c is less than a or c is greater than b. And if you take the function 0 and you do the same thing, you will get 0. Well, sure, but that's not actually a very impressive statement. But that is the closest we can come to making this statement coherent. This is saying, if x is not 0, then delta of x equals 0. They're saying that's the 0 function, and that if you were to integrate, in fact, no, that doesn't even work. We can't even say that 0th function because this isn't a function. This is actually 0 the generalized distribution, and you have to go read a book by Lighthill in order to get all the details on that. Here's an analogy. Calling the Dirac delta a function is like saying the square root of 2 is a fraction, a rational number. Both of these statements are false. The Dirac delta is not a function. It's what's called a generalized distribution. The square root of 2 is not a rational number. It's an irrational number. You cannot write it as a fraction. Now, what these do have in common, besides both being wrong, is that there's a way that they're sort of almost right, in that the Dirac delta is the limit of a sequence of functions. Actually, many possible sequences of functions, just like the square root of 2 is the limit of a sequence of fractions, because 1 is a fraction. 1.4 is a fraction. 1.41 can be written as a fraction. 1.414, likewise. 1.4142. You're getting closer and closer to the square root of 2. And that's not the only way to do it. There's endless ways to approach the square root of 2. So there's 2, 1.5, 1.42, 1.415. You're decreasing towards it. And lots of other ways to approach it. There's an endless supply. And in effect, one could say the definition of an irrational number is to say, take all of these sequences that seem to be approaching the same gap in the rationals, and that entire family of sequences, let's call it something. Let's call it the square root of 2. Well, with the Dirac delta, what we have is, say, a bell curve with an area of 1. And suppose we keep shrinking the standard deviation down towards nothing. It will get narrower and taller, and if in this form, the integral will always be 1. It'll always have a 1 area. Likewise, you take a rectangle. Gn of x is n in that range and 0 else, and that has an area of 1. You let n increase, and it's getting taller and skinnier. Likewise, you could do it with this triangular function. As n gets larger and larger, it gets more and more pointy, more and more narrow, but the area is always 1. All of these are tending towards the same thing, which is the Dirac delta. So the collection of all these possible sequences of functions is what we call a generalized distribution. That's the meaning of delta of x. That doesn't sound anything like being a function. Now, many times the limit of a sequence of functions is another function, but sometimes they're not. The Dirac delta is not a function. It doesn't have values. Just like with the square root of 2, we could say, what's the numerator? Well, the square root of 2 doesn't actually have a numerator because it's not a fraction. Likewise, delta of x doesn't have values. The numerator of square root of 2 doesn't make any sense. So you can say these are distributions, and you can say these are real numbers, and you've made a category big enough to encompass everything. But you can't get away with pretending square root of 2 is a fraction. And likewise, you're going to get into trouble if you try to treat the Dirac delta as if it's a function. The problem is your textbook might not have been careful enough. I struggled with some problems in a quantum mechanics textbook that were just assignments in learning to manipulate the Dirac delta. And I was wondering what's wrong with me when I was being too precise, and so I was noticing that these questions weren't actually making any sense. And I dug into the theory, and eventually I worked out answers to many of them, and some of them, the questions weren't even wrong, they were incoherent. And so I want to spare you some of that grief. So this is a myth about the Dirac delta that I want to just explode right there.